Okay, so this is Lab 4, Rope Physics Spring Mass Lab. We're going to be using Newton's second law to predict the motion of a mass spring system. We're also going to be using the energy principle to give us more information about the system and its motions. The energy principle, as we can see here, will be our change in kinetic energy plus our change in weight force and potential energy and plus our change in spring force potential energy. All of this will equal 0 since we're going to assume that all force transfers are within the system and nothing transfers across the surroundings, and things like air drag are negligible. These are our known constants here. The things we need to find are, we need to know what the spring tension is, so we are going to use the period of oscillation equation to find that information. So rewriting the equation to solve for K, the spring tension constant, we find this equation. We know we can find the oscillation period of the y-axis, and specifically it needs to be the y-axis, we'll go into that later, is 1.519 seconds. So we can find that the spring tension is 6.8 Newton meters. Coming down for the relaxed state of the spring, we are going to look into it that the system is at a static equilibrium, so that weight force is going to equal spring force. Knowing this, we can get this equation, which then we can solve for the relaxed state, which will be 1.127 meters. So let's go ahead and take a look at Tracker real fast so we can get an idea of what our actual motion looks like. We took our x and y positions over here and we put those into a CSV file, which we'll later use to show actual motion versus the predicted motion in a graph. So let's go ahead and take a look at Python. So the black arrow represents weight force and the blue arrow represents spring force. As you can see, the blue arrow ebb and flows a bit with the motion of the spring. And we can see that our predicted motion is looking quite a bit like our actual motion that we witnessed on Tracker. So over here on the right, we see our energy principle. So if we zoom in on it, we see that we get a slight oscillation here of the overall energy change, which was supposed to be just 0. This could be due to the fact that maybe my oscillation calculation, the oscillation period wasn't quite correct, and therefore it's throwing off the equation just a little bit, giving me a slightly wrong spring tension. But we see that it's actually predicting fairly accurately what we were expecting to see. We see that it's staying at 0 or close to 0. We can see that our oscillations of kinetic and potential energy are looking like they're canceling each other out, which again indicates why we're getting almost a 0 or a 0 energy. So, okay, so I made some quick changes to the Python program here. We're going to run it again. And here we are using the CSV file I spoke of earlier, and we are checking our actual motion and position versus our predicted motion and position. And as you can see, they are fairly accurate. Again, the actual motion is bouncing around quite a bit more because of our difference in delta t, our time frame that we're using to take our motions. And you can see here on the graph that we are fairly close to our motions. Part of the issue with maybe not being perfectly accurate with this is that maybe we're getting some air drag that's affecting the system more than we thought, or it's possible that during the oscillation the mass strikes the wall that it's hanging off of and uses drag force to slow itself down a bit. So, as we can see, the energy principle is satisfied. We did get a delta E that was 0 or next to 0, because again, the kinetic energies and potential energies were oscillating. Now, as for the x and y axis, the reason we use the y-axis to give our oscillation period and not the x-axis, we get two different numbers here. The y-axis, it represents more an average energy transfer from the spring force and the weight force, whereas the x-axis would give us a longer oscillation period because it's not affected by the spring force until the very end of its motion, whereas y is always being affected by spring force up and down.